Okay, everybody. Hope you're all loaded up on coffee. And some hot snacks. So let me introduce the second speaker of the afternoon. We have all these little stars here sprinkled in the audience and under the roof. But here's the big Mexican star who will take us on a tour out of our own local solar system and into the galaxy.
Thank you. Well, okay, the subject is somehow different from the main emphasis here, but I will look to galaxy dynamics, but I will formulate actually this problem as a problem quite familiar to us, a problem in scattering or in quantum mechanics, with the method of quantum mechanics. So in a sense, it's quantum as well, right? So, let's start. Now, there is an archive paper, which is this one. And then I will discuss the dynamic of galaxies and all of clusters of galaxies. Actually, the same. Either you think that you have stars or clusters of clusters of galaxies, right? I will refer to galaxies for simplicity. Understanding then that all the results extend to galaxies. Cluster of galaxies. And the fundamental system of equation that governs the dynamics of galaxies is the gravitational Blasov-Poisson system. So this is a Blasov equation, I don't know how you pronounce it. And F is the distribution of mass at point X, position V, right? Actually, it's interesting. It's universally known as a Blasov equation, but some 20 years earlier, it was introduced by Jeans. Jean is a British astrophysicist, and I don't know why it's known as Blasov equation, but actually it should be Jeans equation of Jeans-Blasov equation. So this is the dynamic of the matter of the stars, say, and then is self-consistent. So here is the gradient x of the gravitational potential that is produced by the density of stars itself, right? So this is a closed system, Blasov-Poisson. It's an approximation of the Blasov-Maxwell system. Then I repeat, this is the distribution function that gives the density of matter at a point x with some velocity, so in a phase space. So this is the gravitational potential induced by the self-gravitating matter. And this is the density of matter, right? Which is the integral. And the natural condition for an isolated galaxy is this one. But then under the plane symmetric symmetry will change that approximation. But this is the thing that there is no matter far away, right? So this is the problem. And then this system has steady state solutions, right? So solutions that are independent of time. And there are many. So there are many solutions. And the issue of the stability is an important problem in astrophysics, right? So this stability is a major concern in astrophysics. As I will discuss later, this is closely related to the problem in the plasma physics case. It has to be changed a little bit. So, and then there is a large literature on the stability of these steady states, including a nonlinear orbital stability. So orbital stability meaning that if you have a steady state and you take initial data close to the steady state, you remain in a neighborhood. But orbital stability doesn't tell you more than that, right? And if you don't know how large the neighborhood is, well, then from the physical point of view, it is of interest, but of somehow limited interest, if it is very small. So, and then the basic result here is Antonov. These papers by Antonov 1961 and 1962. And this one true. Antonov, well, he was a Soviet astrophysicist. He derived a famous lower bound. I will come later to this lower bound for stability. And I should say that even in the more recent results, including my own, this Antonov stability bound is essential, actually. It's a very important result. Now, but then, well, there are many, many results, even in the linear case, and some of them, Lemu, Mea, Rafael, this paper in Communication in Mathematical Physics, 2011, and this one in Invenciones Matemáticas in 2012. And well, this is a very nice review, Mugo. This was actually, well, it was an exposé talk at Seminaire Bourbaki, and then it was published in Asterisk. And then, of course, it's very well written, very clear, and there are many things to be learned there. And the main result then is the orbital stability of this system. Right? Now, there were much less is known about asymptotic stability. So actually, what is the dynamic for large times? And this is the problem we would like to study. And then this has been studied in the physics literature, and it has been suggested that, well, in the physics literature is mainly the linearized problem. You linearize around a given steady state. This could lead to damping. So, and this is in particular to gravitational Landau damping. I will go to that. That is to say, to the decay of the induced gravitational force. And what they mean is, well, this concept of mixing, that if you have a continuous of states, they can somehow interact in a destructive way, and then you have damping. Just thinking in the Riemann-Lebesgue lemma, right? The Fourier transform goes to zero of an L1 function, and well, in a very simplified form, this could be what people call mixing. So it was claimed in these papers, those are very fundamental papers too, Linden-Bell, and this, well, monthly notice of the Royal Astronomical Society, 62, then 67, and this one too. And there is a lecture notes in physics. He has a contribution in lecture on stellar dynamics, in galactic dynamics, and n-body simulations. And this is lecture notes in physics of 94. These concern the physics literature. And it has also been mentioned in the physics literature that there could be oscillations, right? That will corresponds eventually to bound states later on. Oscillations, it is an important work of Matur. The same journal, this is an important journal in this area, 1990. And these are two books, Binet and Remen. This is from Princeton. This is somehow a basic reference in this area. And there is also this one, Friedman and Polyachenko, Physics of Gravitating Systems. Right? So if you are interested, you can find the information about the physics of this problem. And well, there is recently some mathematical work in criteria for the existence and for the absence of eigenvalues of the Antonov operator. And this were obtained. And this eigenvalue corresponds to oscillatory solutions of this gravitational Blasov-Poisson system. And well, those are this is a paper in the archive of rational mechanics. And these are preprints here. And there is a nice monograph by Kunze. He's, I don't know, he's in Köln or somewhere in Essen, right? He wrote a monograph in a Birman-Schwinger principle. So there is an analogous here of the Birman-Schwinger principle to count the number of bound states. And then there are cases where it is known that there are bound states and criteria for the absence of bound states, right? Now, what I am going to do is to study the continuous spectrum with the scattering theory methods. So this is my problem, which is complementary to this work, right? Moreno, this another. They all consider different models because there are many models here that you, uh, well, spherically symmetric, you can add an external potential and so on. Right? And then, okay, and then there is the plasma physics case. Now, in plasma physics, the equations are the same. However, here we have gravitation, so it's an attractive force. In plasma physics, could be, attracting or repulsive, depending on the particles you have. But what is more important is that the stationary steady states are different. For example, they will consider often homogeneous states, and in astrophysics, there are different types of states that they consider because of astrophysical reasons, right? Um, and then, well, this is a very famous work of, well, first there is Landau damping, is Landau in 1946, and this actually is a remarkable effect because, well, what is the meaning of Landau damping? You have a plasma, say a plasma of electrons, that are interacting through their own, well, electric interaction, and they generate an electric field. And then they found, and this was a great discovery of Landau, that the electric field goes to zero in time. But there is no dissipation here. And then this bunch of electrons that are moving all around, they adjust themselves to a configuration where eventually there is no electric field. And there is no dissipation here, right? And this appears very often in plasma physics. And this is an issue that has been extensively studied. This decay can even be exponential. There is some Penrose stability bound that plays a role here. And well, a major breakthrough in the nonlinear case is this paper, famous paper of Moore and Villani in Acta Mathematica, where they consider Landau damping in a torus, and they prove that it would also exist in the nonlinear case, and even the physicists were not sure if that was the case. And then, well, if you like reviews, this is Bedrosian is an archive, and then you again, this is from the Journée Équation aux dérivées partielles of 2023. So there's a lot of references in Landau damping with and without magnetic field, right? In fact, the Fields Medal of Villani that he was given partially for this work contributed to attract a great deal of attention in Blasov-Poisson systems. This became a rather famous problem. And also from the physics side, there is this ITER project, which is a large tokamak that you might know is being built in southern France. It's a true international collaboration and one of the few that remain in present circumstances. Right? So this application attracted a lot of interest too. Some of these problems were classical problems in plasma physics, but now they have been studied again, and the numerics here is very important too. So this is the plasma physics case. But then let me mention now all the results, including Villani, are perturbation of homogeneous steady states, right? Which is natural in the case of Landau damping. You can consider in plasma case you can take homogeneous unperturbed problems, right? But then there is Bruno Depré. He's the first actually he gave proof of Landau damping in the linear regime for perturbation of non-homogeneous steady states. It's one paper in Annales Henri Poincaré, and the other one in the Journal of Spectral Theory. Bruno Depré, he's at the Laboratoire Lyon, Sorbonne Université. So Now, this problem has so many aspects, right? Now, it is a remarkable fact that in the presence of a constant external magnetic field, the lambda damping just disappears, and the solutions are oscillatory in time. So you might have a situation where you have exponential decay, you add the magnetic field, and this is not trivial, because if you're in a tokamak, well, magnetic fields are present there. Actually, you have a large magnetic field. So that's in that constant, this is a more important issue, right? On this point, there is a paper that I wrote with Frédéric Charles, Bruno Després, Alexandre Reich. This fact actually is known as the Bernstein-Landau paradox, because, well, the physicists found it paradoxal that you're in a lab, you have something that damps, you put the magnetic field, and it's oscillator. And then this is a study that was done using operator theory methods. So we see this again as a quantum mechanical problem. And actually, this is a topic I will talk about next week. Then there are many references there, and it's a paper in the Journal of Statistical Physics appeared a few years ago. So now what I will do is I will discuss the asymptotic stability then of steady states in the gravitational case, and I will give a proof of gravitational Landau damping, meaning now that the gravitational force and the times derivative, they go to zero. They damp. And eventually we will see that the stars actually follow the orbit, are transported along the orbits of the Newton's solution to Newton's equation with the potential or the force of the steady state. So this will come out of scattering theory. The fact that actually doesn't seem to be known even in the physics literature. Right. So, but then I will make an approximation. I will consider a gravitational Blasov-Poisson system under the assumption that the phase space density is plane symmetric. Could also be spherically symmetric. But there are some technical issues that are slightly simpler here. But this would apply also under appropriate conditions in the spherically symmetric case. So then the density depends only on the first Cartesian coordinate and is symmetric for joint reflection in x1 and v1. So this is the condition of plane symmetry, right? And this is extensively used in galaxy dynamics, and it corresponds to disk galaxies, like our own, like Milky Way. So, and this is a picture taken from internet. This is this galaxy, and x1 is now this coordinate. What I am telling you is that the amount of matter that moves in this direction, or it's here with velocity v, is the same to the one that is here with velocity minus v. This is an alternative to a spherical symmetry. But both of them reduce the problem to one dimension, effectively. In this case, you have to integrate out the velocities transversal to x, which is x1, which is now x. Okay. So then this becomes one-dimensional, and then I will consider a plane symmetric steady state solutions to the gravitational Blasov-Poisson system of this form, right? A distribution function f sub 0 and a potential u sub 0. And then what the astrophysicists do, they take this a function of the energy, right? From a prophetic function phi. Actually, this energy, it's called the microscopic energy because it's the energy of each, well, of the trajectories that you have there, right? I should have mentioned at the beginning that in the Blasov equation, you think that you have a continuum of matter, right? At the scale of a galaxy, the stars have a continuous distribution. So this is what it is. And then I will linearize the gravitational blast of boson system around f sub 0 in this form. And then I introduce this expansion and I keep the first order term. So if I compare which was done earlier, I will consider the linearized equation, not the nonlinear as they do, but this is not going to be only orbital stability, but the precise description of the dynamics. So then the equations are the following. The Blasov equation linearized here. You see, this is now the external. I mean, this is the potential. Well, this is going to be the, okay, this is what I have here. This is the Blasov equation. This is the potential produced by the density of matters. I just took away the deltas, right? It was delta F, delta rho. Now those are rho and F to simplify my notation. And then this is the transport operator along the orbits of the gravitational potential of the steady state, which is crucial here. And then my distribution function is plane symmetric. And then I have to decompose it into the even and odd parts in V in this form. And if I just compute the equation for each one of them, and I take the derivative of the equation for delta F minus, I get that the even part I get in terms of the odd part, and that the odd part is a solution of a wave equation, which is the where this is the Antonov operator, and this operator, the unperturbed part, is minus d tilde square, so the transport operator, and b tilde is, well, this interaction term, right? And actually has been proven that if I have a solution of this, is delta F minus is separately antisymmetric in X and V. So I have more antisymmetry. So then on the end, okay, let's summarize for the steady state of this form, where F sub 0 is a function of energy that satisfies then the celebrated Antonov stability bound. Now this operator, the Antonov operator, is strictly positive with a positive lower bound. And then we see that we are getting into a familiar framework, right? Because we have a wave equation with a strictly positive operator, and then the unperturbed problem is this one. So I have a scattering problem for these two, right? And then this dynamic, the unperturbed dynamic now is just transport along the classical orbits. So this is what it is. Now, which type of steady states? Steady states have been extensively studied. And then, well, if you go to these books I mentioned, well, function of energy of this form, right? You introduce a cutoff, and this is called a king steady state, which is of this form, and this means the positive part. There are astrophysical reasons why you would like to consider these steady states, but then I will not discuss that. But those are very popular, I would say, type of steady states, right? And then, well, there are results on a steady state. There is this paper that I already mentioned here. And then for each positive m sub 0, there is a plane symmetric. It's a variational problem on the steady state, f0, u0, such that, well, rho sub 0 then is well, the density, and u sub 0 are both even. But you shift them to make them eventually even. And m sub 0 turns out to be the total mass. So if you pick a total mass, then you find the state. So they find the state. And then there is enough regularity. This is C1, has compact support in minus R0, R0, I mean the density, and is strictly decreasing on 0, R0. and the potential is C3 is convex on R and is strictly increasing, and it's eventually linear. Mm? Moreover, it's positive, and the minimum of energy is at x equals 0 by translation. So it's a nice potential like that, right? And then omega hat series integral support of the distribution function, and well, this here is defined, right? And the reason, since there is a cutoff in energy, this is a compact set. So we're going to use scattering, but scattering in a compact set. Mm. And then the Hilbert space, H tilde, well, I make it complex value just to introduce the machinery of complex Hilbert spaces, unitary evolution groups. But if initial states, the initial conditions are real, it remains real. Mm. So H tilde is the Hilbert space of all complex valued measurable functions defined in here that are separately antisymmetrics in X and V with this measure. Now, for example, for the first class of a state I consider, phi prime is 0 in the boundary. So this is a singular measure, and this we'll have to take care of that. Mm. Okay. And then what is interesting is that if you take this A tilde, the Antonov operator, the quadratic form in this Hilbert space coincides with the Antonov functional. So this can say is another way to write the Antonov functional that give you the stability. So it's natural to consider the problem in the for the Antonov operator in the Hilbert space that define the stability of the linear stability. So linear stability being positive, there are no exponentially growing solutions, so no catastrophic instability, right? And the steady state considered above satisfy the Antonov stability bound, and then is strictly positive with a positive lower bound, right? So the problem is the following. I have my perturbed wave equation with a positive operator, my unperturbed wave equation in this Hilbert space, right? And then if I use Barman's invariant principle instead of the wave equation, I study the associated Schrodinger equation. Schrodinger type equation, because of course this is not a Hamiltonian, right? I mean, it's not an energy. But then we are in a situation where we can play the game we're used to play in quantum scattering theory. You could try trace class methods, you could try time-dependent ends-type approach, or as I will do, stationary methods. The advantage of stationary methods is that, well, they are constructive. So you give formula for the wave operators, and you can perform eventually a numerical calculation, what is important here. Mm? Right. And then I will repeat the solution of this. This paper is quite a long paper, but it's in archive. And then when you have to, it's very useful to do a transformation to energy angle coordinates, right? Because this is a way to get a spectral representation of the vector problem. Now, then you have the period function. So for every e, the orbit goes from x minus of e to x plus of e and back to x minus of e. And this is, well, you find this in Gorstein book, for example, right? And then this is the period, and this is the angle that you define for x between the two bounds, and for e bigger than a minimum. A minimum is the u sub 0, 0. And recall this is the non-relativistic energy. So this is Newtonian physics. There is also a relativistic version of this. Okay, this is very nice. However, when you we are going to change coordinate energy and angle, but this blows up as you go to the bottom of the minimum energy, right? Because, well, if you decrease the energy, eventually you have a solution sitting in a point, which is just the minimum of the potential. And then the singularity actually could spoil everything here. So you have to control the singularity. And then this is the energy angle variables. For positive V is theta and E, and for negative V is 1 minus theta and E. Actually, if you go to literature, often people call these action angle variables, but in energy is not an action, right? You have different units. So I rather call them energy angle variables. And in these variables, A sub 0 acts in this form with periodic boundary conditions. And you have 1 over the period square, right? And so then you can construct a spectral representation in a space of this form where beta mean is 4pl. L this comes then from a Fourier transform. So you have this periodic operator, you Fourier transform it, and then you get this type of representation. Mm? The multiplicity would change, and then you have to rearrange it, but this is somehow technical issue. But a Fourier series, to be more precise. Some people call the series transform, but it's Fourier series. Right? And then it's multiplication by the variable, and it is here, right? So then this is a setup where you can stationary scattering theory. It's not simple, but because of singularities in particular, but this can be done. And then what are the results? Well, the absolutely continuous spectrum is a set of bands, and this is the spectrum of the Antonov operator. The bands appear because you take the Fourier series, right? The intersection of the singular spectrum, meaning the point spectrum and singular continuous, with the absolutely continuous spectrum of A tilde is contained in a closed set of measure 0 that is characterized. Still is an open question to know if there is singular continuous spectrum here or not. There could be, but well, this is a matter of future research. Later on, as the points where identity plus a compact operator is not invertible. So it's precisely that. So we know exactly where it's lying, if we can solve the question, of course. And then generalized Fourier maps are constructed. They are partially isometric from H tilde into this spectral representation space with the absolutely continuous subspace as initial subspace. And then you have the diagonalization. And then the whole operators exist and are complete. And they are isometric. They have undertwining relations and also Berman's, this is important, the stationary formula are proved. And this opens the way to numerical work, if you would like to do it. And then Berman's invariant principle of the wave operator holds. What it means that if you rescale both the aperture and the vector energy, so to say, so replace A sub 0 by phi of A sub 0, A by phi of A for an appropriate function of phi, the wave operators are the same. And a very important one, you take a square root of A tilde and a square root of A sub 0 tilde. So, and then with this result, it's possible to describe the large time asymptotics in a precise way and to prove that the gravitational Landau damping actually holds. So, okay, large time asymptotic. For simplicity, let's take just initial state here and the delta F main of the solution to the Antonov equation of this form. So I have taken the time derivative of 0 equal to 0, but could take a more general initial state. Then I can construct some G plus minus 0 by taking the joint of the wave operators and define G plus minus of t in this form. And well, I have got roots, and then because of this Berman invariant principle of wave operators, then I know that for large time, the solution to the Blasov-Poisson system is asymptotic to the solution of the Berthold problem, which is just transport. Right? So that is to say, for large time, the solution is asymptotic to the solution of the free Antonov wave equation. Right? So asymptotically, the phase space distribution just follows the trajectories I think it's an interesting result. Just follows the trajectories of the orbits with the Newton's equation with the potential of the stationary state. So when you look at the sky, then this is what the stars are doing. Right? I say that I haven't found this in the physics literature. It is a precise description of the dynamics. Of course, this is linear, but it's much more precise than saying there is a neighborhood where the solution lies, right? So this is first consequence. Now, and then Landau, gravitational Landau damping. Well, remember, just to remind the notation, this delta F was the perturbation. This is then the potential produced by the density of stars as related to the distribution function in this form. And then the gravitational force is defined, of course, in this form, minus the derivative of u. And then if I consider a solution to the linearized gravitational Poisson system, again, for simplicity, the even part I take 0, and the odd part absolutely continuous. Right? And then this is gravitational Landau damping. So in L2 sense, remember that the density had support in minus rho sub 0, rho sub 0. So in L2 sense, then, well, the force goes to 0, and then the time derivative of the force goes to 0 in L2 sense, and then by integration I get the points-wise N infinity estimate for the potential and for the time derivative of the potential. It has to be like that, because if the trajectory is asymptotic to a solution of Newton's equation transported along a solution of Newton's equation with the potential of the states, the induced gravitational force will need to go to 0. Right? But it's now proven using this scattering theory result. Now, there is only one previous result. This paper, I don't know how to pronounce, maybe Hatchik or whatever, Rhein, Schrecker, and Straub, damping of versus oscillation. This is the paper where they prove axial eigenvalues. In that paper, they consider, well, the spherical symmetric case, not by symmetry. And they take a steady state with a fixed external potential. There is a fixed external potential and a steady state, and the steady state is small. In that situation, the dynamic is somehow controlled by the external potential. And then they prove this decay estimate, right? This is, well, already is decayed in the mean, but the force could even grow like a power and then still be true. Right? But it's already result. This was the only one I know, previous result. So how do you set up the perturbation analysis for this problem? Right? Because it's quite different from Schrödinger equation. Right? Now, it's convenient to work first in energy angle variables. Now, in these variables, the perturbed Antonov operator has a simple representation, and you can construct explicit representation. On the other hand, the transformation to energy angle variables is singular, as I already mentioned, right? Where the orbit degenerate to a point, which is the elliptic point of this Hamiltonian, microscopic Hamiltonian. Right? And then this has to be analyzed. And again, what I remind you somehow, okay, this is the appropriate Hilbert space, and the plane symmetry in the x, v variables mean this symmetry in the theta variables. So you have to consider functions with this symmetry, with the anti-symmetry in the x, v representation. So this is what you do. And I recall you that this was the after problem, and then I define the perturbation. Okay, there is a unitary transformation to those new variables. I don't give the formulas, but you can imagine how that would be done, right? Now, so I mean, when you go to energy angle variables, this is very nicely represented, but this is somehow ugly. So actually, you have to work with this formula. Now, okay, I will work with a space of Hilbert continuous functions. C alpha, I sub 0 is the interval of energy is that I have, right? Remember, I have a compact energy interval. So Banach space of Hilbert continuous function of order alpha, and more than that, the closure of the same infinity functions. So in this space, you can approximate every compact operator by finite rank operators. And then this is the basic perturbation object. But then why do I take spaces of Hilbert continuous functions? Well, I am in a compact set. Now, in quantum mechanical problems, there is, the solution travels to infinity. And then you take weighted spaces, L to S, L to minus S, that somehow give more weight locally. And then this is the way it is done. But actually, what is important is that these weights in quantum mechanical case make the spectral function or spectral family of the unperturbed operator Hilbert continuous, locally Hilbert continuous. And what we actually use in the proof is this local Hilbert continuity. Now, we don't have any decay, there's no infinity, but we take from the scratch a space of locally Hilbert continuous functions. But of course, locally Hilbert continuous functions don't like very much singularities, right? And then this is the reason of technical problems, right? Oh, B tilde, well, B tilde is the, okay, B tilde was this integral operator I defined at the very beginning, which is the perturbation. There is a formula, but maybe it won't tell you very much. It's an integral operator that defines the perturbation, the interact, I mean, in this Antonov wave equation, remembering the Blasov equation, there is interaction term with the derivative of the induced gravitational potential. It corresponds to that. And then you transform it. Maybe I go back at the end to the formula and I show you. But what it is it represents the interaction of the stars among themselves due to the gravitational potential that they themselves produce. This is the meaning it has. And then there is a formula for that. Okay? And then I never really define this U, but think of it as a Fourier series, taking the Fourier series and change the variables in an appropriate way. Hmm? Then this is the object I wish to study. But then this V would vanish eventually, so the velocity when the particle reach both x minus of E, x plus of E, then this vanish. And for some of the states can also vanish, so that you have to be careful of that. And then, okay, let me give you some results, some theorems to give an idea of the proof. Then for every alpha 1 between 0 and 1, and alpha 2 is more than 1/2, and C in the resolvent set of halves of 0, Now this operator actually sends Helder continuous functions into the C hat, so the closure of the same infinity functions. And this is true on spite of the singularities of the coordinate transformation. For some other model, this could not be true, and then all of this would fail to be valid, right? And then this function is analytic in the operator norm between the two spaces. The norm at infinity goes to zero. I go away from the spectrum. And this operator is compact between the spaces. And then this is the initial setup of perturbation analysis. No. Let's see is just the Helder continuous functions. But then you take the same infinity Helder, okay, not only Helder continuous, same infinity. And you take the completion in the norm of the Helder continuous functions. So it's smaller than C. And it's much nicer in particular because in that case, if you take, it's a parallel. You can take the closure, you can approximate the space by a sequence of spaces of finite dimension, and then you can approximate every compact operator by operator of finite range. And then you can perform the analysis for the existence of the limits on the real axis using some complex variable argument. There are a number of technical issues that I am skipping under the rug actually. So I keep away from the thresholds. The threshold is the beginning of the end of each one of the bands. And then if both of them are smaller than 1/4, rather small, then the following limits hold. This limit exists in the uniform operator topology between these two spaces, and the convergence is uniform for gamma if I take any set that is a finite union of bounded and closed intervals containing gamma, so any compact set in gamma, if you like. So this is what you have to prove. And these functions then are analytic. They are defined as G of gamma when I am in the resolvent set of zero, and as the limits when I go from above and below. So I define here with values in bounded operators between the spaces. They are analytic in the spectrum, in the resolvent set, and Helder continuous with their rather small exponent. All these limitations come from the singularities in the transformation. Right? And it's uniform in compact sets, and these are compact, right? Here. Now, okay, so this is what you prove. And then there are conditions. Okay, I forgot to mention that the first class of states are a function of energy are called polydrops, by analogy with some gases which are called polydrops. So that's the name it has. And then if I have these conditions here, right? Yeah. And then n plus minus gamma in this gamma that I just defined. One is an eigenvalue, right, of this operator. So the Bach set, yeah, this is how it is characterized. And then n plus is equal to n minus equal to n, and is independent of alpha as long as alpha fulfill these conditions. And then the singular spectrum is here. So the point spectrum embedded in the absolutely continuous, and if there is any singular continuous spectrum, it will be here. So far, interesting open question is to see if there is singular continuous spectrum or not. And the reason why it doesn't follow from these results is that I will need the exponent to be bigger than 1/2. If it was bigger than 1/2, then I could say that this set n contain only eigenvalues. And then it could not be singular continuous, and then it will be done. But the restriction is because, well, I mean, the difficulties do not just disappear, right? They somehow remain. It's a nice transformation to energy angle barrel, but it's singular, and then, but this is an interesting open question. Would be nice to see if actually these classical models, if they do have singular continuous spectrum. Then theorem, then M is this bad set union the thresholds, right? And also at the threshold, again, this transformation blows up. So coordinates. So then I have to exclude them. This is a close and of Lebesgue measure. It's very important. It's a closed set and is of Lebesgue measure. And to prove this, I have to use some complex variable results that are true because this space C hat actually is, well, can be approximate. I mean, in that space, every compact operator is limit of finite rank, and actually there are results for complex value functions that you extend to this infinite dimensional space, and you can do that because you can approximate this compact operator by finite rank ones. This is why this particular space is taken. And the point spectrum in gamma is contained in N. I don't mention it here, but also the singular continuous spectrum is contained here, if there is any, right? And well, the sigma P denotes the eigenvalues, all the eigenvalues, not the closure, I mean the eigenvalues. And moreover, the eigenvalues in gamma, if they exist, they have finite multiplicity by compactness of the problem. Mm. And then they have to introduce some further restrictions, the functions that are here in my space, such that this is bounded. For example, if they have compact support away from the E sub 0 when this function vanish, if it is a polytrop. Mm? And then these are the generalized eigenfunctions eventually. And you see there is this inverse. So if you would like to compute them, then you have to compute this inverse, which amounts solution of identity plus a compact operator. This is an advantage. It's an old issue in scattering theory, stationary scattering theory, that there are very nice methods, but if you wish to really compute, then you have to do this. 2 minutes only. Okay. Well, so I will skip maybe very quickly the proofs. Then I take this limit. This is basically, I wish to use Stone formula. And then I computed this. F here is Fourier series. This limit exists, and well, I can, these functions are Helder continuum, then I can take sharp values, but I cannot show very much this. Then first I define the general Fourier maps in function of these forms, and this is the definition, right? There are, here these factors are to appear when you construct the spectral representation. So, and then you define, you have this, actually, this is the spectral operator, spectral measure. This goes to multiplication characteristic function, and you define it 0 in the complement of the absolutely continuous subspace. And this is partially isometric, and well, of course, it's always a problem to prove the completeness. In this case too, you have to work and prove completeness. And then when you have diagonalization by the general Fourier maps, let me show quickly. Okay, now what have I shown? Shown that the method of scattering theory provide a detailed description of the asymptotic dynamics of the galaxies. Mm? And as far as I know, the first time that it's proven that actually the Landau damping in a strict sense actually holds in the gravitational case. Because in the gravitational case, considering homogeneous states make no sense. Right? And now these methods are beginning to be used in the study of Blasov boson system, in the plasma physics case and gravitational case. I think it's a nice area for mathematical physics, this type of questions. And they play important role. And there are other situations like the Blasov boson Fokker Planck, where there is absorption. And then this is scattering problem for non-self-adjoint operators. But I never stop because, thank you. Oh. Well, before, I think I forgot to thank the organizers for the invitation and to congratulate Volker for his birthday. After so many congratulations, right? Congratulate you too. Okay. Yes, for me, it is. I think it was a bit later. Well, let me see. Let's do it slowly so I find it. Oh, should be here. Oh, here it is. So what is here? In a sense, this integral is the distribution of momentum, right? Right. And then this is a factor, and then there is the velocity there. This is what the perturbation is. It's linear. It's linear. It's linear. Oh, okay. So the original equations are the Blasov-Poisson. Let's go to the very beginning. So this is the Blasov-Poisson, and this is nonlinear as such. And then what I did is, let me show you again. Okay, I take now f sub 0 was the distribution of the static, the stationary one. I consider epsilon delta f. I put this in the nonlinear equation, and then I get this. I have linearized, right? So even epsilon, right? Yeah. And you just order 0 is just a stationary solution. Order epsilon is this one. So to use a scattering theory method, you have to linearize. Well, there are methods in nonlinear scattering, but well, that's a different story. They don't give so precise results, and they just tell you, I mean, existence of nonlinear operators and so, but not formulas you can actually use to compute, if you like to. Oh, f of 0, okay. You take the nonlinear Laplace system, and you look for a solution which is time independent. And then this is f sub 0, and it has associated u sub 0 that follows as an integral of f0 over the velocities. Different? Oh, there is a host of stationary solutions. Well, okay, yeah, let's go to again to the original equations. Okay, here are the equations. Now first, I take the time derivative equal to 0. Then I have to solve this equation where u is this. In principle, well, it's a system, but actually it's only one equation because you can put this in here and then you have only one equation, right? And then, well, you just take out this term, this one you put here, and you find the solution to it. Mm? But then, okay, I mean, there are so many and then you pick one. Right. It does depends a lot because I use a lot. I mean, but this is those are stationary solutions that are studied by the physicists, right? Uh, well, I mean, what I really need is that the associated potential have nice properties. And I need that, I did not mention it here, but there is a period function. This period function in this case is monotonic in energy. Because otherwise it will be complicated to make the change of coordinates. Now, if it is non-constant, you can do local scattering theory, take a piece of energies where it is a positive derivative, another piece where it is negative, and so on. If it was constant over an interval of energy, then there you cannot perform the change of coordinates. Right? And actually, it's an important issue in Hamiltonian dynamics to have monotonicity of a period function. It's a problem that has been studied. And there are conditions, and in this case, in this model, the conditions are satisfied. Certainly, there are solutions where all of this is false. In particular, if the exchange of coordinates will be too singular, then I will not be able to set up perturbation analysis in a space of Hölder continuous functions because the interaction will take me out of that space, right? But those are models that are studied by the astrophysicists, right? Well, thank you.